what we're going to do in this class is we're going to look at some things that you probably saw before back in the Algebra 2, or maybe some stuff you saw in pre-calculus. And we're just going to look at it a little bit in a little more detail and look at some other aspects. And what we're going to do is we'll look at some things with factoring for the first few weeks here. Then we're going to jump into something called rational expressions and look at algebraic structures, the systems with the expressions. Essentially looking at fractions and functions in which you have a polynomial over a polynomial. And then as we progress, we're going to look at some applications throughout the course. And then we are going to look at graphing as we get about midway or halfway through it. So a lot of these things, again, you've seen before. And I don't really care so much how you do something. I'll tell you from time to time if there is something that comes up where I want you to work it a certain way. But for the most part, as long as you show a reasonable amount of work, you show logic, you show some reasoning behind your response, I'm okay with that. And the way that I teach is I teach in a way that I want to take you from understanding as opposed to just memorizing your way through a problem. Because if you memorize your way through a problem, what happens when your memory fails? You can't do the problem. But if you understand how a problem works and your memory fails, chances are you're able to reproduce the solution if you forget a formula. So that's kind of the approach that I want to be taking here over the next few weeks. And the first thing I want to jump into is this idea of factoring. Factoring forms a foundation, a bedrock for a lot of things that we're going to be doing throughout the whole entire course. And factoring, it's one of those topics which is kind of hard. Thankfully, factoring is hard, because if factoring wasn't hard, you would not have the internet. You would not have your cell phones. You would not have this online commerce, because you wouldn't have what's called encryption. And the whole entire encryption system that we have is based upon the fact that factoring is complicated. So if you're struggling, hey, it's okay. It's meant to be hard, but it's definitely doable, at least what we're going to be looking at here in this course. And whenever we're factoring, we can talk about factors, just take it real easy here. We can look at things like numbers, 2 times 3. But that's not really what we're talking about. What we're talking about with factoring is we're talking about factoring polynomials. And a polynomial, as the name would suggest, there's many nomials. You got polynomial. And a type of polynomial might be something like x squared plus 5x plus 4. Or another type of polynomial might be something like 5x plus 1. Now, there's lots of ways of how I can classify a polynomial. I can classify a polynomial based upon the number of terms that it has. If I have a polynomial with 2 terms, it's known as a binomial. If I have it with 3 terms, it's known as a trinomial. And I can keep going with this naming scheme. I go up to looking at 4, looking at 5 terms, 6 terms. But for the most part, we look at trinomials or binomials. And there are going to be some times as we get later into the course, we'll look at not just 2 terms or 3 terms. We might look at a polynomial maybe with 6 terms or 7 terms. Now, I can also look at it in which I have a polynomial with 1 term, just a monomial, maybe something along the lines of 6x to the 7th power. So I can classify it by the number of terms that it has. I can also classify it by the degree of the polynomial. And the degree of the polynomial, that corresponds, when you look at the x value, you look for the highest exponent, and we're looking at integer values. So here, this is going to be second order, which is also known as a quadratic. So this is a trinomial, but it's also known as a quadratic. This right here, again, this is a binomial. But I can also classify this as being something to the first power. That's known as a linear polynomial. And here I have something that's to the 7th power, and I also have a monomial out of it. So I have linear, I got quadratics, I got cubics, I got quartics, I have quintics. Oh my! I can keep going with this naming scheme. And a quintic is just a degree 5 polynomial. I can also take this binomial and I can also maybe have it into the 3rd. And I can also classify it as a cubic. Okay, so there's lots of ways of how I can designate, classify these different types of polynomials. And you'll see these names pop up as you go throughout the course. And what we want to do is factor polynomials. Now, a polynomial, again, is just many terms put together, right? Combine them with an addition or a subtraction. What I'm not talking about, at least not for the time being, is I'm not talking about things like it's the 1/2 power or something to a negative power. Okay, these are not going to be polynomials. Now, we'll talk about these later on, but it's not for our discussion for the time being. So, when I'm factoring, I'm really talking about factoring polynomials. So, if I have a polynomial like 5x to the 2nd power and then 2x, factoring, what's that based upon is the distribution property. We have this, where I have A times the quantity of B plus C. And a lot of times you might have heard maybe distributing, expanding, or maybe something along the lines of foiling, where I'm just going to take the A and I'm going to multiply everything inside. And when I do this process is known as expanding. When I go in this direction, when I compact it, repackage it, that's what's known as factoring. So one of the ways of how I can factor is I can factor by finding these common terms amongst the terms itself. Take it and yank it out. And I just follow whatever this formula is telling me to follow. So I look to see what's in common. So from here, I see what's in common is an x. So I can take the x and I can just yank it out. And there's nothing else I can do here with factoring this polynomial. So if I can't do anything else, I can call a polynomial irreducible. It's not factorable. And just like when I would have with numbers, let's say if a number is 7, I can't factor 7 like I can factor 6, where 6 can be factored as 2 times 3. I can't do that with 7. The only thing I can do with 7 is I say 1 times 7. 7, this is a prime number. Well, when I'm looking at polynomials, I have a similar terminology. I can look at something like x squared plus 4, and I can't factor this. I'm set. I'm done. There's nothing that this will factor as. This is known as a prime polynomial. Prime polynomial because we cannot factor it. And I'll give a little disclaimer with real values. All right, we'll talk more about that later on, what that means, but I just can't go any further with it. But this polynomial, I can definitely factor. I can definitely take it and express it as a product of 2 non-trivial functions here, x and 5x plus 2. And if I had something else, let's just say 10x to the 3rd power, we have 50x to the 4th power, I can play the same game. And even if I was to have it not as a binomial or if I had it in terms of a trinomial, I can still play the same game. I want to find common terms. Here I see I have a 5. 5 times 2 gives me 10. 5 times 10 gives me 50. And here I have 5. So I can take the 5, take the constant, and I can pull it out. But this polynomial, it's not a prime polynomial. I can keep factoring it further. So when a problem says factor a polynomial, oftentimes what it's referring to is factoring it all the way, not just part of the way. So you want to completely factor it, yank everything out. So here I do see an x squared, and an x to the fourth, I know that's going to be an x squared times an x squared. And an x to the third, I can take it and recalibrate it as an x squared times an x. And there I see that a value that we have over here in the distribution property. Or I take the x squareds, and I can yank them all out. Now, these polynomials, if I just look at this group, I can do some factoring here, but I can't do any more factoring when I look at all three terms. So I'm essentially done with the problem with the factoring. So I can look for these greatest common values, factors amongst the terms, and this is one of the ways of how I can pull out the common terms and factor it. Let's say if I have x squared plus 5x plus 6. And our goal again is I want to take this polynomial and I want to factor the polynomial. Again, there are reasons why I want to factor the polynomial, and we'll talk about those here in a moment. But to factor this polynomial, this is my goal. My goal is to take this and rewrite, when I'm looking at a quadratic, as a product of two linear polynomials. Let's take a moment and let's really look at to see what's being played out here. If I was to expand out, do the foiling process where I have first, outer, inner, last, and let's just throw an example up here real quick. X plus 2, x plus 7. So I would say maybe x times x, which gives me an x squared. And then I can say 2 times 7, that would get me and then here I'll have 2x, and here I'll have 7x. And if you notice, if I was to do this, I created myself a smiley face. So it's all about perspective, guys. You know, try to find the humor in it. Try to always find the good things in life. It's always easy to find the bad things, but even a crazy foiling problem, factoring problem, I guess there's some good in there. Okay, anyways. So you would have your first, outer, inner, last terms as you're going about the process. Here, this would collapse down, and you would have 9x squared, or excuse me, x squared plus 9x plus 14 when you expand out. Here, if I did the exact same process of expanding out, you would have x squared, then you would have b times x, a times x, and then a times b. And if you notice, here I have two terms. And you might recall these are alike terms because they have the exact same variable raised to the exact same power. I can also take the x and I can factor it out. There's that distribution property I can apply right here. Now, look at what I have on the left-hand side and look what I have over here on the right-hand side. And right in between, I have this thing. What's that called? Equal sign. What does it mean for something to be equal? It's the same. So what I have on the left is what I have on the right. They're identical. They are the same. So what that means here is this. If I'm going to factor this polynomial, The way that I factor the polynomial is, well, the 5 needs to be that term, and the 6 needs to be that term. Now, by just taking a moment and understanding how this thing works, this gives you a wealth of information. This tells you how to factor an infinite amount of polynomials. In fact, these type of polynomials, which satisfies this property, which have a 1 in front, they are referred to as monic polynomials. Okay, now you might hear me throw that term out from time to time. That's all I mean when I say monic. There's just a 1 in front of the x squared. And these polynomials, you're really, really easy to factor, relatively speaking, to something a little more complicated. Because all I got to do is this. I don't look at that. All I got to do is cast my attention to the constant term here at the very end. And I factor the number. So I would look at the number 6, and I would factor it. I can see that it will factor as a 2 and a 3, but it also has a factorization of a 1 and a 6. But it also has a factorization of a -2, -3, and a -1 and a -6. So after I look at all the factors which would comprise 6, all I'm going to do next is to see what would add up to a value of 5. So this right here gives you the numbers to work with. This right here locks it in. And I can see very quickly it's going to be a 2 and a 3 because that's what's going to sum to the value of 5. And our polynomials factored. So if you want, write yourself a little step-by-step play as how to go about this problem. First, check to see if there's a 1 in front of the x squared. And make that your step 1. See if it is a monic polynomial. Step 2. If it is a monic polynomial, don't worry about anything else for the time being. Only worry about the last term right here. And what you're going to do is you're going to factor this term and look at all the different ways of how it can factor. Then you're going to glean through the list and look to see what would add to the middle term. Now, again, I have two things that could occur here. It's possible that I could factor this polynomial, and then I can express it as a product of a linear term times a linear term. That's a possibility. The other possibility is I'm not going to be able to factor this. And if I can't factor it, I call it a prime polynomial or an irreducible polynomial. And I don't worry about it. I go about my business. I just can't do it, at least not for the time being. So, first things first. Don't worry about this. Don't be intimidated by it. Just worry about the -20. Take the -20 and look at all the different ways of how you can factor this particular number. Okay, so one way of how I can do this is to take a -1 times it by 20. That would work. Another way is to say -2 in a 10. That would also work. -4 in a 5. That would also work. But I can also say 1 in a -20, or 2 in a -10, and a 4 in a -5. So once I have my list done, the next thing is I just want to go through my list. And I just want to see if I add up the factors, which one sums to the value of -1. And if I can't find it in my list, well, I know the polynomial is going to be prime. So add those up, I get 19. Here I get 8. And here I get 1. Now that's really close, just a little difference of sign. And another thing that I want to do when I'm factoring is I want to use a little bit of strategy. This is really far off, so probably don't want to look at this. That's kind of far off too, so I probably want to look at that one. But if I just reverse the sign, I'll get my -1. So I have 4 to -5, -1, and that's exactly what I have up here. So I'll have x plus 4x minus 5. And the process is complete. Now, this process that I'm teaching you, we're going to use this process later on in the course, and when we start looking at degree 6 polynomials and degree 7 polynomials, degree 20th polynomials. I'm going to show you how to factor those. But right here, this is the foundation of how to go about that process. So you can use another method if you want. You can use the cross method, the box method, whatever method, that's fine, in order to factor the polynomial. So these kind of polynomials, not too bad. We got this. So let's crank it up a little bit more. What if I had something that's a little bit more complicated? So this polynomial, it's not a monic polynomial. So I got a little bit of a problem here. If I just had a 1 in front, pretty easy. So how do I work these kind of situations? Now, again, what I want to do is I just want to pause for a second, and I want to see how this problem is really working. If I'm going to factor this polynomial, the way that's going to factor is it must factor as a times x plus b, cx plus d. And I'm going to do something very similar. All I want to do is just take this and I want to expand out. Because again, I'm just trying to understand how this thing works. Well, when I expand out, I'm going to have x squared, ax, and d, bc, x, and then finally bd. Common terms, like terms, pull the x out. Now, again, I have a polynomial on the left side. I got a polynomial on the right side. And in between, I got this equal sign. The equal sign means it's exactly the same. So what I have on the left must be the same thing I have on the right. Otherwise, they're not equal. Well, what that means again is here I have an AC, and that's got to correspond to 6. And here I have a BD, and that's got to correspond to a -2. And then in between, I got this big old mess. I got to figure this thing out. But notice what that's saying again. If I want to factor the polynomial, I don't have to shoot in the dark and try to hope that I hit something. Just by taking a moment to see how this works, it gives you a wealth of information. If I want to factor the polynomial, what I want to do is this. Look at the first term, look at the last term, and I just want to look at the factors. See, 6 needs to be factored as a times c, and -2 as b times d. So I'm going to take this and break it apart. So all the factors which I can make with 6, I can say 1 and 6. I can say 2 and 3, and that's about it. For -2, I can do 1 and a negative 2. I can do negative 1, and I can do a 2. Okay, so if this factors is going to be one of these combinations up here with a 1 and 6, 2 and 3, or these values. So the way how I can pinpoint this down is I can do something called a brute force method. It's also known as the method of exhaustion because you get pretty exhausted when you get done doing it. I just want to look at possibilities. So I can say 6x and an x, and I can put these two things together and maybe use those pieces. Or I could say 6x minus 2, x plus 1. Or I can write it that way. Another thing that I could do is instead of saying positive 1, I could use a negative 1. But again, I'm not for certain where I need to put the negative 1, where I need to put the 2. Maybe it needs to go over here. So for each one of these possibilities, I'm generating two factorizations that I need to really investigate, really need to explore to see if this is going to lead me to anything useful. Also, instead of using a 1 and a 6, maybe it's going to factor as a 2 and a 3. You can only use a 1 and a negative 2. So likewise, maybe a 2x and a 3x. Or maybe you need to go over here with negative 1 and a 2. So what we're doing is we're just looking at all the different possibilities. And if this factors is going to have to factor as one of these up here. And it doesn't work, that means it's not going to be a polynomial that can factor, it would be a prime polynomial. Okay, so all we're doing here is we're listing out now. Here's where the brute force comes into play. I know, beyond a shadow of a doubt, that whenever I start expanding this out, my first term is going to be 6x squared. Every single one of these, I know it's always going to be this. How do I know that? That's how I'm making these. If I look at the factors for 6, and I use the factors for 6, whenever I expand out, I'm always going to create a 6. Okay, that's trivial. I mean, there's not much there. And likewise, since I'm using the factors for negative 2, when I expand out, I'm always going to get a negative 2 out of it. So the beginning's great, the end, okay, but what I'm really interested in is what happens here in the middle. You know, it's kind of like life, guys. In the beginning, God created. That's awesome. I love that. And you know what's going to happen in the very end? God wins. What's really interesting, what happens here in the middle? And that's your story. What happens right here in the middle? Well, in order to unlock what happens here in the middle, this method is going to require me to go ahead and expand out. Okay, so I'm going to have 6x times x. I got that. But here I'm also going to have a negative 12. And here I get a x. And what I'm shooting for is a minus 1x. That's not it. So that's not my story. That's not how it factors. So again, I would try for the next one. I would say, okay, 6x times x, guaranteed 6x squared. I got it. So I'm really looking for are these linear terms and see how they're being constructed. And here, I have 4x. That's still not a minus x. So that's not going to work out either. And I can keep going through this whole entire problem. I have a 12x minus x. That's not going to work. 6x, 2x. That's also not going to work. So what that tells me then is these possibilities are out of the question. It's a method of exhaustion because you get pretty exhausted when you get done doing it. Just a lot of different possibilities to check. Okay, so here, if I was to expand out, I would have 6x squared minus 4x plus 3x minus 2. And I got to ask myself, when I combine my like terms, do I get minus 1? So what do you do when you find what you're looking for? Stop searching. You found it. You're done. And this is how I can factor doing this systematic approach process of elimination. Now, there are other things up here too that you want to use some strategy when you go about your factors. And some other strategies that I could have done was this. Do you see how you have a even term here? 2 is also an even number. If I was to put this together, is there a common term I can factor out? Absolutely. I could have pulled out a 2 here from all those values. Could I pull a 2 out from all these values up here? I can do it here. I can do it there. But what about here? By using that strategy, using that insight, you can actually take your list, and it looks long, but you can actually reduce the amount to check. 6x with a minus 2, probably not going to work. So I don't even need to go through the hustle and bustle expanding it out. It's more likely not going to work. I can just cross it off my list. Same thing here. I got a common factor between these two terms. I can get rid of that. I can get rid of this one. And I can get rid of this one. So I can take my list and I can reduce it down by half, which makes it a lot more manageable. Okay, so these kind of polynomials, I can factor it by going about this process. Now, are there other ways you can do this? Absolutely. But I'm showing you right here is the method of exhaustion. Now, this method we're going to expand out later in the course, in about 10 weeks. And we're going to look at how we can look at how to factor not just quadratics, but cubics and quartics and quintics. Oh my! Degree 6, degree 7. There's going to be no stopping us, but we're not quite there yet. Now, again, this is a monic polynomial. Since it is monic, all I'm going to do is focus on the 9, a 3 and a 3. And if I add up a 3 and a 3, I do get 6, which is exactly that term right there. So know exactly how this factors. It factors as x plus 3 times x plus 3. And I can take this and I can compress it down a little bit more. I can rewrite it as x plus 3 quantity squared. Now, if I have x plus 5 quantity squared, look at what this thing's not. This is not x squared plus 5 squared. Real common mistake. I see this happening all the time on the exams. Don't make this mistake. If I have x plus 5 all squared, that's x plus 5 x plus 5. And if I expand out, if I FOIL this thing out, first, outer, inner, last, I'll have x squared, 5x, another 5x, and 25. Because 5 times 5 is 5. I have x squared, and I got 2 of these. And I'm going to write it a little differently. I'm going to say 2 times 5x. But the main takeaway, first off, is these two things are not the same. Look what's missing. So if I have something that's squared, I just can't put the square on the terms. That's not permitted. I need to actually expand out. In general, what happens here is if I have a plus b all squared, this is going to correspond to a squared. And you will pick up a b squared. Guys, don't forget about the intermediate term. 2ab, right there in between. And if, by chance, if it was a minus, what you get out of it is a squared minus 2ab b squared. So if you see a polynomial which has this type of structure to it, you can factor it really, really quickly. So here's a perfect square. And when I see a perfect square, my spidey sense goes off. I'm thinking, okay, maybe it's one of these. Maybe not. But I wanted to consider that possibility. And then here, I do see that there is an even number, 8. It's not 7, it's not 5, it's 8. So I know that I can take it and I can rewrite it. And if I can write this number as 4 squared, we don't have to go through this process of elimination. I got it right here. So as I'm going about my problems, there are certain patterns we want to recognize so we can factor it a whole lot easier and not make a problem more complicated, more difficult than it really needs to be. Now, next time we're going to look a little bit more at some of these special factors and also look at why even do this? What's the point of doing this? And we're going to look at that in a little bit more in detail. But if you need anything, come on by. Other than that, you guys have a great day. I will see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.